Welcome to Lesson 9B, Introduction to Particles, Part 2. I'm going to discuss some highlights from the PowerPoint presentation and then give a little bit more detail about colors and visible light. In these highlights, I'm going to list particle classifications and sizes from largest to smallest. Water drops are generally between about 2 and 10,000 microns, and 10,000 microns is 1 centimeter. Human hair is generally between about 30 and 200 microns, depending on the color of the hair, as I said in the slideshow. Pollen is typically between about 10 and 100 microns. Non-glowing particles that are visible to the naked eye are particles greater than about 70 microns. And I will put a star by everything that I want you to know or memorize, if you want to use that term. You'll need to know these for the closed book part of the quizzes. Mold spores are generally between about 3 and 40 microns. Remember, the shafts can be larger than that, and the heads can be even larger. A glowing particle visible to the naked eye is greater than about 10 microns. Both of these cases are for healthy eyes. Coarse particles, also called inhalable particles, or PM10, particulate matter less than 10 microns, are, as the name implies, less than about 10 microns. Particles less than about 10 microns can get into your lungs, whereas particles greater than about 10 microns get stuck in your nose hairs or in the back of your throat. They don't get into the lungs. Fine particles, also known as fines or respirable particles, or PM2.5, are generally less than about 2.5 microns. Respirable is not the same as inhalable. Respirable means they get deep into the lungs, all the way into the tiny little bronchial tubes and even some of them down into the alveoli. Whereas inhalable, they get into your lungs, but typically get caught in the upper region of your lungs in the larger bronchial tubes. In between these two is inhalable coarse particles, and these generally lie between 2.5 and 10 microns. We can call them PM 2.5 to 10. So these are still coarse particles because they're not small enough to be respirable, but they are inhalable. So they call them inhalable coarse particles. Supermicron particles are particles greater than about a micron, as their name implies. These are primarily from grinding, pulverizing, and crushing mechanical processes. For example, talcum powder. They're also called dust. Submicron particles are particles less than about a micron. These are primarily produced by combustion. For example, smog and tobacco smoke, which can get really small, like 1/100th of a micron. These can get very deep into the lungs, into the alveoli. I want to mention briefly our body's removal mechanisms. First, for particles in our bronchial tubes, typically between about 1 and 10 microns, we have mucus plus cilia. The mucus traps the particles in the lining of the bronchial tubes, and then the cilia are little hairs. They push them up into your throat, and then you swallow them. For particles in the alveoli, typically ones that are less than about a micron, the removal mechanism is macrophage. These are white blood cells that digest the particles in there. And remember from the PowerPoint slides, some particles cannot be digested, like asbestos and certain kinds of tars and stuff from cigarettes. Continuing with our sizes as we go down in size, bacteria are typically between about 0.2 and 20 microns. You can have some fairly large bacteria. People classify ultrafine particles, or UFP, as particles that are less than about 0.1 microns. That would be 100 nanometers. And these will become much more important later on when we talk about filters. So we can talk about filters that can remove ultrafine particles. Viruses are generally much smaller than bacteria. Viruses can be as small as 0.002 up to as large as about 0.5, although those are rare. Coronavirus is around 0.125 microns. Nanoparticles, this is in the news lately because they're starting to use them for lots of things. They're defined as particles less than 0.05 microns, which is 50 nanometers. You'd think that nanoparticles were down to about 1 nanometer, but they're actually anything below about 50 nanometers is called a nanoparticle. And finally, atoms. We're not going to go all the way down to electrons or anything, but 2 to 6 angstroms, where 1 angstrom, some people put that little circle on the top. 1 angstrom is 10 to the minus 10th meters, or 10 to the minus 4th microns or micrometers. Now I want to talk a little bit more about colors and visible light. Remember, light can be treated as either particles of photons or as a wave. And so the wavelength of light we'll call lambda. We'll consider this a light wave. And for visible light, it ranges from about 0.33 microns to about 0.7 microns. This would be lambda. The 0.33 microns is down in the violet range, and the 0.7 microns is up in the red range. And then you have the whole rainbow colors in between. I remember in high school physics class, my teacher brought in a prism. I hope all of you had the same experience in high school, where you have white light coming in from, say, the sun, which has all the colors, but then it splits due to refraction into all these colors. So the white light splits or refracts into all the colors of the rainbow: red, orange, yellow, green, blue, and violet. Through all of these bend, but the red doesn't bend as much as the blues and violets. Violet is the one that bends the most. So if violet bends more than blue, why isn't the sky violet? Rather, it's blue. I have visited some planets where the sky is not blue. Thank you, Captain Kirchhoff, for that tidbit of information. Well, on Earth anyway, it turns out that all three of these, green, blues, and violets, bend a lot due to particles and scattering. This is called Rayleigh scattering, by the way. In the sky, you have sunlight that is scattered, kind of like the prism, due to Rayleigh scattering. And this is scattered from air molecules and other small particles acting like individual prisms. Blue and violet are the ones that scatter most. And then if you combine the green, blue, and violet together, they combine to form the blue color of sky. If you look directly into the sun, of course, it's white. But if you look away from the sun, it'll be this bluish color typically. So that's why the sky is blue. The similar thing, why is the sky red or orange, yellow during the sunset? And that's because, again, here's not a real great sketch, but the red light doesn't scatter very much, whereas all the other colors scatter. So reds, yellows, and oranges come kind of straight through the atmosphere, whereas the rest of the colors reflect. So that's why you see beautiful orange, yellow, red sunsets. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.